This is the second part of section 6.5. It's a logistic differential equation. We're going to talk about logistic growth. Now consider the case of a population P with a growth curve as a function of time that begins increasing and concave up as in exponential growth, then turns increasingly concave down as it approaches the carrying capacity of its habitat. And what they're referring to is a logistic curve. Now let me draw a logistic curve for you and explain what they're talking about in that statement. Here's a graph. Imagine uh, a pond, and we throw 1,000 fish into the pond. And here's represents at initial value of 1,000, 0 yields 1,000. The fish are going to multiply, and their growth is going to increase very rapidly. And once the population hits half of what's called the carrying capacity, and let's say the carrying capacity is 10,000 fish, because of oxygen limitations, opportunity for food, all kinds of environmental, because of environmental effects, there can only be 10,000 fish in this pond. A pure exponential growth would say that the pond could have an infinite amount of fish because exponentially the curve goes up to infinity. Well, that's not realistic. Ponds can't hold 50 billion fish. There's not enough oxygen, there's not enough food to support that life. Well, once the population hits half of the carrying capacity or the maximum population, so once the population would hit 5,000, that's when the population would be increasing the fastest. And as soon as it gets over 5,000, the rate is going to slow down. And then eventually the population will level off at 10,000, which would be the maximum amount of fish that could be in the pond. So here's a logistics curve, very roughly. We have seen that the exponential growth at the beginning can be modeled by a differential equation, dp over dt, or the rate at which the population is increasing over time, is equal to kp for some k greater than 0. That's a exponential growth. That's not the logistic growth. If we want the growth rate to approach 0 as p approaches the maximum carrying capacity, m, we can introduce a limiting factor of the maximum population minus the actual population. So the rate at which the population grows is relative to how much population is there based upon the maximum that the pond, let's say, can handle. So let's say that m is the 10,000 that we said before. And let's say that the population is at 8,000. Well, we're going to have a multiplying factor right now of 2,000. And then let's say the population reaches 9,000. Now we have a factor of 1,000, which is much smaller than 2,000, of course. And let's say we have 9,500. Now we have a factor of 500. So as the population gets closer and closer to the carrying capacity, the rate at which the population is increasing is going to decrease because the multiplier, or the factor that is going to get smaller and smaller as we approach the maximum capacity. This is the logistic differential equation. Before we find its general solution, let us see how much we can learn about logistic growth just by studying the differential equation itself. And I don't know if I'd included that in here, and I actually didn't. I went right to example 4. The growth rate of a population P of bears in a newly established wildlife reserve is modeled by the differential equation dp over dt. So here is, let's go back to that general one. I don't want that. Let's see if I can just arrow over. There we go. The K is our constant value, and in this case is 0.008. P is the population, and 100 is the maximum that this wildlife preserve can have as a population. Where T is measured in years. So P is in number of bears, T is in years. What is the carrying capacity for bears in this wildlife preserve? Well, by the formula, the answer is 100 bears. What is the bear population when the population is growing the fastest? The population will be growing the fastest when it reaches half the carrying capacity. What is the rate of change of the population when it is growing the fastest? So here's the rate, and it's growing the fastest when the population is 50. So we plug, whoops, too many zeros. We plug 50 in for P. 100 minus 50, and I'm going to get that answer, and I'll be right back. And I'm back instantly. And I have the answer. The answer is 20 when we multiply all this out. So the answer to letter C is 20 bears per year. In example 5, we're tracking a moose population. In 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park, Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach carrying capacity in about 25 years with a growth rate of, and here's their growth rate, and you can see that the maximum population they're predicting is 1,000. According to the model, what is the carrying capacity? Well, it's 1,000. With a calculator, generate a slope field. Well, we don't really do that. That's not necessary. Solve the differential equation with the initial condition of P of 0 equals 61 and show that it conforms to the slope field. We're not going to worry about the slope field in these. Here is the slope field. And we have the method that we're going to use to solve this. We start out with the equation, and they're going to multiply by dt and divide by p, 1,000 minus p. And you can see that happens right here. To solve this, you're going to take the integral of both sides. We're going to use partial fractions to integrate the left side. That's what this is all about. A ends up being 0.001, and B happens to be 0.001 also. In the next line, they're multiplying by 1,000. So if you multiply 1,000 through here, multiply this by 1,000, you get 1 over P, 1 over 1,000 minus P, and you get 0.3 when you multiply both sides by 1,000. The integral of 1 over P is the natural log of P, and the integral of this is natural log of 1,000 minus P. They don't worry about absolute value here because we're not going to have a negative population. They take the integral to the right side. If you multiply, let's see what they've done here. Multiply everything by -1. You get natural log of 1,000 minus P, minus natural log of P equals, and this becomes negative. Now the reason they multiply both sides by -1 is to get this statement right here, so that you can divide 1,000 minus P divided by P and get 1,000 over P, and then P over P would be 1. That's the reason this happens right here, so that P is the denominator, not 1,000 minus P. In this step, we go solve for the natural log, so we have e to this entire exponent equals 1,000 minus P over P. They've added 1 here. And finally, they get the constant in this step right here, setting P equal to 61, T equals 0. We find that e to the negative c equals 15.393. So there's your constant. And then, let's see, there's a couple ways to finish this one. You can take the reciprocal of both sides and then multiply by 1,000. And there's your final solution. The graph conforms nicely to the slope field. And you can see the shape that I drew. You throw 1,000 fish in here, or whatever the initial value would be, the population is going to increase very rapidly until it hits about half the carrying capacity, and then the rate starts slowing down and eventually leveling off to that carrying capacity. Here's the particular solution right there. There's the solution to this differential equation. The general logistic formula, the solution of the general logistic differential equation, if you're given this differential equation, the solution looks like this right here. Where A is a constant determined by an appropriate initial condition, the carrying capacity M and the growth constant K are positive constants. Here's some examples out of the book. In exercise 23 through 26, logistic equation describes the growth of a population. In each case, find A, the carrying capacity, B, the size of the population was growing the fastest, and C, the rate at which the population is growing when it is growing the fastest. So the carrying capacity is 700. The rate is the population is growing the fastest when the population is 350. And if you plug 350 into the rate, you get 980 individuals per year. Now I've included some more exercises from the book in exercise 27 through 30. Solve the initial value problem using partial fractions. This says use a graphing utility for the slope field. We don't necessarily need to do that. I've chosen number 28. We have dp over dt equals 0.008p times 700 minus p with the initial condition the population's 10 at the time when time equals 0. We separate the variables. We integrate the left side by using partial fractions. It turns out A ends up being 0.0014 and B is also 0.0014. By taking when we take the antiderivative, we get 0.0014 natural log of p, 0.0014 natural log of 700 minus p. Once again, the population is not negative, so I don't have to worry about absolute value. We get 0.0008t plus c. Let's see, what do we do? If we divide, now what I've done here is, this is the rounded answer, but if you take 1 divided by 700, you get that answer, and if you leave that in your calculator, if you take 0.0008 divided by the actual answer, you get a nice 0.56. Now, if you use the rounded answer that we have here, when you divide everybody by 0.0014, you don't get a real nice 0.56. So I encourage you to use the exact answer, not the rounded one. By properties of natural logs, we can write natural log of p over 700 minus p. Again, we want the p to be the denominator. So if you multiply both sides by -1, I can raise this whole thing to the -1, which it will allow it to be the reciprocal, 700 minus p over p. If we solve this equation, we get 700 minus p over p equals e to this entire exponent. And then next step, we can simplify this to e to the -c times e to the -0.56t. If we take 700 divided by p and p divided by p, we get 1 here. And we add 1. Now, e to the -c is just c. C is c no matter what we do to it, really. And let's see, what do we do here? I can multiply by p, and we can divide by this entire thing to get the solution here, with the exception that we need to find c yet. Now I've used the initial condition. I plug 10 in for p and 0 in for t. Well, e to the 0 is 1. 1 times c is c. Multiply by 1 plus c, divide by 10. We get c ends up being 69. So here's your final answer. P equals 700 over 1 plus 69 e to the -0.56t. And that is the solution to this differential equation all the way back up here. That's the solution. And there we have it. In exercise 3132, a population function is given. A, show that the function is a solution of a logistic differential equation. Identify K and the carrying capacity. So we have P of T equals all of this, which is very similar to the formula that we're given. It says this is a logistic growth model at K equal 1 and M equal 200. And there's you just have the corresponding parts, and that's really what you have to show. In letter B, estimate P of 0, explain its meaning in the context of the problem. If we put 0 in for T, we get 200 divided by 1 plus e to the 5.3. If you work that on your calculator, it's approximately equal to 1. And what is the meaning of it? Well, initially one student had the measles. And there we have it.